All right, chapter 15 is going to be a little different than the past few chapters. The past few chapters we've been talking about different molecules or different functional groups. In this chapter, we're going to be talking about different types of isomers. We've already learned something called constitutional isomers, in which you have a formula, but you can draw several different structures for that formula. All right, so isomers basically is a different compound, but you have the same formula. Okay, a constitutional isomer is that it differs in the way the atoms are connected. So if you have a molecule that has an oxygen in it, you can either draw a molecule that has an aldehyde or a ketone or an alcohol, any type of compound, or an ether, any type of compound that has one different uh, kind of group in it. It has the same formula, but the structures are different. Okay, so here's a perfect example. These compounds both have the formula C6H14, but they are not the same compound because the atoms are connected in a different spot. This methyl group is connected to carbon 2. This methyl group is connected to carbon 3. All right, so here's another example where you can have different functional groups. You have the same formula, so C2H6O, C2H6O, but this is ethanol and this is diethyl ether. Same formulas, but different structures. Those are constitutional isomers. This chapter is about what's called stereoisomers. These are basically the exact same molecules, except they differ from each other in 3 dimensions. Okay, in 3-dimensional space, they differ. They have the same functional group. They are identical in every way. In fact, you can actually name these compounds exactly the same. So if you look, here's a compound. You have 1, 2, 3, 4 carbons in a row. Okay, so it's a bute, and you have a double bond on the second carbon. So this is 2-butene. Look at this compound, same thing. It's a bute with a double bond on the second one. This is also 2-butene. However, in 3 dimensions, they are not the same. One of them has the methyl groups on the same side, which we learned is called the cis compound. And then we have a molecule where you have methyls on the opposite side, which is the trans. Okay, so you have cis and trans. These are not the same molecule. They are the same molecule, but yet they are not the same molecule because in 3 dimensions they are different. And that's what stereoisomers are, where you can have the same exact compound, but they differ in 3 dimensions. Okay. However, we're going to talk about, so we've already talked about double bonds, the cis and trans. We're going to talk about something a little different. Okay. And this is called chirality. See this word chiral? This is pronounced chiral. That CH has a K sound, not a ch. Okay, so chiral or achiral compounds. Okay, and I kind of want you to kind of take your hands, your left hand and your right hand, and just kind of have them face each other. Have the hands face each other, and what you'll notice is that they are mirror images of each other. If you were to shine your right hand into a mirror, the reflection would be your exact left hand. Okay, so if you kind of hold them up side by side and move them back and forth, you can see that they are mirror images. Okay, well, that's great. You're like, well, they're hands, right? So they're pretty much exactly the same thing. Well, they're not really the same thing. Okay, your right hand is a right hand. Okay, and your left hand is a left hand. If they are not interchangeable, it's not like if you chop your hands off and you sewed your left hand on your right arm and your right arm on your left hand, it would not be identical. It would look weird. You would have a right hand on your left arm. It's not like these hands are interchangeable. I can't put them on any arm. Your right hand is your right hand. Okay, and our bodies are like that. Our right side is the mirror image of our left side, but they are not interchangeable. Okay, your arms, your legs, your kidneys, your brain, your lungs, your bones, everything in your body, you have a right-handed version and a left-handed version, and they are not interchangeable. You can't put your femur on your right side and replace it for your femur on the left side. They don't hook together properly because they are specifically made for the right side. Okay, and that's what chiral is, and molecules have this, and pretty much our bodies are like this. Everything in our natural environment is like this. Most of our amino acids and our sugars and things like that in living organisms all use the left-handed version of the molecule rather than the right-handed version. People don't know why. This was just by chance, but in evolution, for some reason, the left-handed version of things won out over the right-handed things. So things, move and twist in a certain conformation because of the fact that we only have one of these handedness of our molecules inside of our body. Okay, so this kind of shows you that if you shine, your right and your left hand are mirror images. They are not identical. You cannot superimpose them on top of each other. If you try to put your palms up and try to put them on top of each other, your thumbs do not match. Okay, if you flip your right hand over and your thumbs and all your fingers match, but notice one's palm up and one's palm down, they're not mirror images. Therefore, it's called chiral. So pretty much a mirror image of anything, and it's not superimposable, is what's called chiral. Okay, socks, for example, the mirror image of a sock is identical. You can superimpose them. So they are said to be called achiral. So there are things in our world which obviously are achiral. There are even molecules which are achiral, like acetone is a perfect example. The mirror image of acetone, you can superimpose it on top of the original image. Therefore, it's not chiral. It's what's called achiral. Okay, so molecules have this, and to test if a molecule has it is you need to draw the molecule in 3 dimensions, draw the mirror image, and try to align all the bonds and atoms. Now, if you have a model set, it'd be very helpful to have that. I do have a few available in class, so the next time we meet in class, we will make molecules so that you can kind of I'll put them on top of each other and see how this works. Okay, so to superimpose a molecule and its mirror image, you can perform any rotation, but you can't break any bonds. Okay, so here's an example of water. Okay, here is the mirror image of water, and notice this molecule is superimposable on top of this one. Therefore, this is an achiral molecule. Okay, all right, now let's look at a chiral molecule. I'm sorry, this is also achiral. Sorry. Here's the mirror image. Imagine I take this molecule and I shine it in the mirror. The reflection would look like this. The chlorine is going to be here. Let's call this oxygen would be over here, and let's call it bromine. Bromine is over here, all right? And then you have a hydrogen up here, and this hydrogen in the back is the hydrogen in the back. You can turn this molecule around and flip it over, and notice all these atoms superimpose on top of each other. Therefore, this is achiral. This is an achiral molecule, all right? Now, let's say you have 4 different groups. This is key. All 4 groups are different around the carbon. Here's the mirror image, okay? No matter what you do, no matter how you align it, it will not be superimposable. Notice your hydrogen superimpose and my yellow superimpose, but look, green goes with red and red goes with green. If I were to flip this molecule over and match my green and red, then my white and yellows will not align. So notice this is the identical molecule. It's a molecule that has a hydrogen, bromine, chlorine, and fluorine all attached to the carbon. It's the same exact molecule, but in 3 dimensions, they are not quite the same, okay? So this is what's called chiral, and molecules have this. And these compounds where the mirror image is not superimposable is what's called an enantiomer, all right? Let me grab a pen real quick. Okay, enantiomers, that's how you pronounce that. So if the mirror image, so on this slide, these 2 compounds are called enantiomers of each other. All right, one's the left-handed version, one's the right-handed version. It doesn't matter what's left and right. It's not like, oh, well, this is the left and that's the right. It's just basically saying it's like hands, it's like handedness. All right, in fact, chirality in Latin means handedness or means hands, it's something like that. Okay, a molecule is not superimposable on its mirror image. I'm sorry, a molecule that is not superimposable on the mirror image, it's called a chiral molecule. So if the mirror image is not superimposable, it is chiral. And we call them enantiomers. Okay, the key to this is that you have to have 4 different groups around your central carbon. And we're going to call it a chiral center or a chirality center. All right, molecules can contain 0, 1, or many chiral centers. Okay, so this is the quick, easy way to determine if you have a chiral center. First of all, you need a carbon that has a tetrahedral carbon specifically that has 4 different groups on it. Okay, not necessarily 4 atoms. I mean, it could, but we'll kind of show you an example in a bit. But this is a chiral center because you have 4 different groups around the carbon. Okay, if I had 2 bromines, if I had a bromine here, okay, then I have 2 of the same groups, therefore then it would be achiral. Okay, but I don't have that. I have an iodine, 4 different groups. Okay, here's an example where you have kind of the same atoms, but technically they're 4 different groups. You have to look at the whole group. So here is my central carbon. Notice I have a hydrogen. I have kind of this ethyl group. We'll call it an ethyl group, but in reality it's not really an ethyl group. I've got a bromine, and I got this propyl group. These are 4 different groups. They are not the same groups. Therefore, this carbon is chiral. The mirror image of this would not be superimposable on top of it. Okay, and you can draw this molecule. Let me show how you can draw this. 1, 2, 3, 4, 5, 6, and you have a bromine here. I'm going to have the bromine wedging out. So here's your bromine, okay, and your hydrogen is going back. Okay, the enantiomer of this, okay, would be where you have where the bromine is going back instead of forwards. So here's your bromine, and here's your hydrogen. Now, these molecules are not that's a hydrogen right there. These molecules are not superimposable. If you were to make these molecules, imagine if I took this molecule and I flipped it over, the bromine would be coming out, but it'd be coming out on this side over here. Okay. A lot of people can't see this. A lot of people can see this. If you can't see this, the best thing to do is to make models. And like I said, when we get to class, we'll make models and we'll start looking at these things. Okay, so a carbon atom bonded to 2 or more like groups is never chiral. That's considered achiral. Okay, CH2 and CH3 groups have more than 1 hydrogen atom bonded to the same carbon, so those carbons are never chiral centers. All right, a C that has multiple bonds does not have 4 groups around it, so it is never a chiral center. Okay, it might still be considered a chiral kind of compound, but it doesn't have a chiral center. Remember, a chiral center is where you have 4 different groups around it. Okay, so trying to locate chiral centers is pretty easy. Basically, look for a carbon that has 4 groups around it, and just make sure those four groups are not the same. Okay, so here's a carbon. Let's see the 4 groups. We've got a hydrogen attached to it. We've got a carboxylic acid functional group. We got an alcohol functional group, and we got a carbon with an OH and a carboxylic acid. So those are 4 different groups. And then if we look at this carbon right here, same thing, hydrogen, a carbon with all of this stuff on it, an OH group, and a carboxylic acid group. That's 4 different groups. So you have 2 chiral centers in this case. Okay, ephedrine, same type of thing. Here's the carbon. We've got this aromatic ring on one side, a hydrogen, an OH, and then this big old thing. All right, that's for the chirality of this carbon. This carbon has a hydrogen, a nitrogen, a methyl, and this O aromatic with hydrogens. Okay, so you have 2 different chiral centers in this case. Okay, how to draw the 2 enantiomers of a chiral compound. I kind of just showed you that, but we'll look at it again. All right, here's 2-butanol. This is a chiral center. How do we know? 4 different groups, a hydrogen, a methyl, an OH, and an ethyl group. All right, and the way you show it is by showing these wedges and dotted lines. You have to put it in a tetrahedral structure. So kind of get to know this. If you memorize this kind of structure, you'll always be able to draw a tetrahedral structure. So you have these 2 are in the plane. These 2 lines are in the plane. Then you have a wedge and a dotted line are always kind of making a V form to it. All right, the one that I drew is just a different formation, but it's the same type of compound. You can see the 2 in the plane are right here. And then you have your wedge and your dotted line in kind of that V form. Okay, so here's one group. So what would the enantiomer be of this? The enantiomer would be if you just switch these 2 groups. That's the quick, easy way of doing it. Okay, or spin it around and do a mirror image, or you could just switch them. There's more than one way of doing this. Okay, so here is kind of taking this and showing you the mirror image. This is the enantiomer. Okay. Okay, I'm going to stop the video for here and we'll start back on the next video on 14.5.